Welcome to this AI agent reasoning and decision making seminar series. And we think it's a very good idea to sort of sharing this research development reasoning about this large language model reasoning and particularly agent as well. And we have this um, schedule which really focused on two parts. One is more some like a foundation model reasoning and the mathematical solvers building on top of large language model, or maybe because using traditional formal language. And then we also have a talk focused on agent as well. And so this is sort of schedule for the following 2 days starting today. And also after that, in 2 weeks' time, we will also have an industry session, which we have guest speakers from Google DeepMind and also Chen who is the leader of the Chen large language model. And also we have people from Huawei as well, and talking about from the industry perspective, how can we actually tackle language model reasoning and agent. So without further ado, I would like to um, start with our first speaker is Professor Song from UC Berkeley. She's the expert on security and privacy, and recently she's quite interested on this particularly AI and also the security related to AI, and also she's going to talk about today is talking about the formal mathematical reasoning. And I guess this formal mathematical reasoning also provides a very a good method for safeguard large language model from the security perspective. So let's welcome Professor Song to give us a talk to tell us a bit about how she can review this formal mathematical reasoning, particularly given the fact that large language model become quite good at solve some of the problem.
Great, great. Thank you. So let me share screen.
Yeah, I'm gonna stop that.
Okay, great. Can you see my screen?
Yes.
Okay, great. Yeah, thanks a lot for having me. Yes, my name is Dong Song. I'm a professor in computer science at UC Berkeley, and also a co-director of a campus-wide center called the Berkeley Center for Responsible Decentralized Intelligence. So today I will talk about formal mathematical reasoning, a new frontier in AI. So this talk is mainly based on a paper in collaboration with with many of the co-authors listed here, talking about how to move forward on this new frontier in AI for using AI for formal mathematical reasoning. Okay, great. So it's been exciting to see AI for mathematics in the area of large language models. We have seen a lot of recent developments making progress in the space. And why do we care about AI for math? So for a number of reasons. So we talk about reasoning. So math will be very important. It will be very helpful for complex reasoning and planning. And also math is a foundation, for example, for AI for science and for many other STEM disciplines. And also in terms of security, it's also math and formal verification. It's also the cornerstone for building provably safe and secure systems. So far, what we have seen is that most, in terms of using AI, in particular large language models in math, most of the community has been focused on what we call the informal approach to math. Essentially here, as an example showing here, these LMs are trained and they directly then are used to solve math problems. And in certain cases, they can also use certain tools. But overall, so far the main approach has been training and then fine-tuning these large language models with these kind of data sets to have LMs to improve their abilities for solving math problems. And in particular, really exciting recent progresses that we have seen using inference time computing and also RL-based approaches. We have seen really rapid advancements with the recent 0103 and also even like a DeepSeek R1 and so on these reasoning and coding benchmarks. So this has been really impressive. However, what I want to point out and emphasize here is that while on one hand, we have seen these amazing advancements for AI for informal math, but however, we do need to pay attention that these approaches do have certain limitations. So one is data scarcity. So current the AI for math, they are still limited to certain like data-rich domains, for example, for pre-college math. And for advanced math, there is much less data, and current models have more difficulty in tackling advanced math. And another really important aspect is that while, again, these LMs have shown really impressive performance on these coding and reasoning benchmarks, but however, ultimately this type of approach lacks what we call verifiability. So they can provide solutions, but in general, these solutions can only be evaluated by comparing with the ground truth, and this only limited to problems with certain like numeric solutions and so on, and also not applicable to most problems actually in advanced math. And while we have seen huge progress made due to scaling, either scaling in pre-training or scaling for post-training and inference time and so on, but we do believe that scaling alone cannot solve these limitations. So this motivates us to essentially argue for another approach in essentially complementary to this the mainstream approach so far with the AI for math. So what we argue is, in addition to the progress we are making for AI for math, it's also really important for the community to make progress on AI for formal math. So formal mathematical reasoning is grounded in formal systems, such as first higher order logic, dependent type theory, and for computer programs with formal specifications and so on. So these formal environments, they can help verify proofs. So they enable proofs to be written and validated in these formal environments, and also then can be also used to provide automatic feedback. So the verification can enable rigorous evaluation of reasoning, and also learning from feedback can help mitigate the data scarcity problem that I mentioned earlier. So here I want to briefly mention that actually, so in the community, we started this effort a while back, even like actually in the last wave of progress in deep learning. So back 6-7 years ago, so my group was among the earliest to actually use deep learning for theorem proving. So this is a paper actually in collaboration with Ilya and others from OpenAI back then. That was in iClear. That we showed that by using deep learning back then, with of course much simpler models and smaller models, it can help improve automations for certain steps in theorem proving. So so back then we showed that deep learning can help with theorem proving, but back then still we the technologies were much more limited, and the compute was much more limited. So now fast forward, with the recent advancements in large language models and the orders of magnitude increase in compute and so on. So we do believe that we are now reaching an inflection point for AI for formal math. So in addition to what the mainstream AI community has been focusing on, which is AI for informal math, we believe that now it's actually a really good time to actually have the community to also focus more efforts on AI for formal math and so we can now be hitting an inflection point where we can also make rapid progress in the area of AI for formal math. So we to help bring the community together to make progress on AI for formal math, we have released a paper recently, which you can see at this URL, providing an overview and overall roadmap for formal mathematical reasoning, a new frontier in AI. And we welcome feedback from the community as well. So in the rest of the talk, I will essentially give an overview and for the open challenges and directions and the roadmap that we have laid out in this paper. So when we talk about AI for formal math, so essentially here we can utilize various formal proof assistance, such as this theorem provers and so on. And there are many different different systems for theorem provers. For example, listed here, this is an example with Lin. And you can formalize mathematics, for example, like this in Lin. So when we use AI for formal math, essentially there's a workflow. And so once we have the formal theorem statements, we want to produce formal proofs using theorem provers. And this step, essentially, this is one of the steps that we can use AI to automate this theorem proving step. And then the produced formal proof and the verified theorems, they can then go into this formal math library. And also, there's an important step where we can convert informal math to formal mathematical statements using what we call formal auto-formalization. So in this workflow, as I mentioned, AI can help with multiple steps. So one of the key steps is given a theorem statement. Essentially, we need to conduct a proof search to search through the proof trees and then to find, in the end, a valid proof. And we hope that using AI, using these large language models, and also hopefully we can construct these proof agents that can then help automate this proof search step. And also, another important step that AI can help is this auto-formalization, where we can have these large language models and so on, this frontier AI, to automatically translate informal math statements in natural language into formal math theorem statements. So while most of the community has been focused more on AI for informal math, it is nice to see that there has been some progress by certain leading groups. So for example, in the recent success of Alpha Proof, which achieved the silver medal level, almost close to gold level for solving IMO challenges by Google DeepMind. This Alpha Proof actually does utilize theorem proving in its key steps. So, so with that, I hope I have showed you why we should care about AI for formal math, even though the whole community has been making really great progress for AI for informal math. And now I want to briefly introduce some of the open challenges and future directions, how we can make this happen, how we can really hit this inflection point to make rapid progress for AI for formal math. And in particular, I'll talk about these open challenges and future directions in several areas. So first is data. And in particular, as I mentioned, in general for math, and actually, in particular, actually for formal math, we do have an issue of data scarcity. So for example, here, we can see that for example, for training code llama, there's like it has code from like 500 billion. Essentially, the training data set has about 500 billion tokens. But however, if we look at all these proofs in available proofs, essentially we have order of magnitude less of training data available for these proofs. And hence, it's really important that we develop various methods to address the scarcity of formal data. And luckily, we do have a number of promising directions how we can improve the availability for these formal data. In particular, we can utilize several directions listed here. So first is to create data with auto-formalization. So this auto-formalization essentially trains these large language models to then automatically convert informal math into formal math statements. Given that we do have a huge amount of informal math, like with textbooks and various things and so on. So with this auto-formalization, it can successful auto-formalization can help us to then produce automatically produce these formal math statements. And of course, this itself is an open challenge that I will discuss in more detail later. But it's there we have seen exciting progress recently on utilizing these essentially feedback loops to improve the these large language models for auto-formalization. And also, so again, so recently, AlphaProof also has been able to enable this step of auto-formalization to generate like 100 million formal problem statements. And this has also significantly contributed to their success in their recent IMO success. And also another part contributing to this IMO recent success by alpha geometry, which provides another example of generating synthetic data to address the data scarcity problem. So in this case, alpha geometry generated 100 million synthetic theorems and proofs using geometric rules, which helped alpha geometry to also successfully solve challenging geometry problems in IMO. So the another promising direction for addressing the data scarcity is with the data synthetic data generation is what we call neural conjecturing. So the idea is that we can develop models to generate conjectures for theorems and lemmas, and then using theorem proving to try to automatically prove these conjectures. Then the generated successful proofs and the validated conjectures, which are now theorems and lemmas, these can then be added to the to the library of math statements and proofs, and this can help produce additional data to further help training the models for both actually for better conjecturing and also proof generation. So far we have seen recent progress on doing this for simpler, relatively simple lemmas and theorems and so on. So we do hope that more, and we are optimistic that more progress can be made here, that we can significantly improve the scalability and the difficulty level of the theorems that we can conjecture and prove in these methods. So that's the open challenges and future directions for addressing data scarcity problem. So now I will briefly talk about open challenges and future directions in the area of algorithms. So there are many different algorithms challenges that we need to address. So for example, for auto-formalization, how do we scale auto-formalization? How can we do the proof search more efficiently and effectively? And how do we exploit hierarchies in theorem proving? And how we can actually learn mathematical abstractions, and how to utilize existing mathematical knowledge, and also how to reconcile the specialist and generalist approaches. So I'll briefly go through this list. So first is how do we actually do auto-formalization at scale? So when we do auto-formalization, actually there are a number of challenges, because when we do this auto-formalization, we don't really have ground truth, so we don't really know whether the auto-formalized statements are actually correct. We need to evaluate them, and we need to develop good metrics to evaluate these auto-formalized statements. And also, we need to be able to automatically validate these auto-formalized statements as well, and ideally using the theorem prover formal steps and so on. So the hope is that we, for complex auto-formalization tasks, we can actually break it into smaller steps and then interact with the formal system to help with this. So for evaluating auto-formalized statements, this actually is quite challenging for several reasons. So first of all, of course, we cannot rely on human evaluation. This doesn't scale. But for like auto-formalized statements, oftentimes there are different forms, different correct ways to do the formalization. And automated equivalence checking itself actually is non-trivial. So, so in order to address this, we need to actually utilize the like theorem prover, this formal verification systems, and with the hope that we can iteratively improve this auto-formalization by leveraging the feedback from the theorem prover as well. So another challenge is how we can actually do proof search more efficiently and effectively. This, of course, is the key, one of the key goals for using AI for formal math, for theorem proving. So there are many different aspects and components what we can do for improving the essentially the capability for proof search. So just like what we have seen, that inference time compute, scaling up inference time compute has been very helpful in improving the general reasoning capabilities of these models. We hope that scaling up test time compute can also help scale up the search, the proof search, and which also is a very natural fit. And also, ideally, we want to develop better value models to help assess and prioritize different proof goals and different parts of the proof search trees. And also, we want to develop systematic evaluation of models, search algorithms, and have parameters so that we can develop more, develop better models for proof search. So right. So as I mentioned earlier, so far we have seen these scaling test time compute can be very effective for improving reasoning capabilities of models, and as in O1, O3, and also in like, for example, the recent alpha proof. And so with the theorem proving, this is a very natural fit. By scaling compute during proof search, this can help us to improve the capability of proof search for the models. And also, so another important aspect is to essentially how we can direct this and prioritize the proof search better. And in particular, we need to develop better value models that can help assess and prioritize the proof goals. So one key challenge and future direction is how to better train the value model, and how we can also get so potentially getting better data and using RL can help with these. And also, so currently, with the current approach for AI for formal math, for example, using DeepSeek prover and so on, they generate the whole proofs directly, actually, without really utilizing much proof search. So incorporating different search algorithms, such as Monte Carlo tree search and other methods, we hope that we can do systematic evaluation of these different algorithms to develop better solutions. So another open direction, open challenge and direction, future direction is that we want to better exploit hierarchies in theorem proving. So especially in theorem proving, when you have a complex theorem, usually even with manual proofs and with mathematicians and so on, usually these complex theorems are broken down into high-level proof goals, for example, different high-level lemmas and so on. And then, so essentially, the complex theorems are decomposed into smaller, smaller goals and so on. So it's important that as we do AI for formal math, we also develop models with these type of capabilities that can decompose high-level proof goals into smaller goals progressively. And also another important aspect, as I mentioned, is that so we are not arguing to use AI for formal math to replace AI for informal math. In fact, there is a natural synergy between AI for informal math and AI for formal math. And it's important to combine both, essentially combine the flexibility of informal reasoning with the rigor of formal reasoning. So in particular, so for example, with the informal theorem statement, we can then try to auto-formalize it, and also then can use then in the end can use the formal verification and theorem prover and so on to validate that. And with the informal theorem statements and the models for informal math, it can help generate, for example, proof sketch as informal proofs, and this also can then be used to then be converted for formal proof sketch, and in the end to generate verified formal proofs. So this way, the informal math part can help with the scalability and also the flexibility and high-level intuition for generating these formal proofs in the end. But with the formal proof, it can help essentially provide the verification for these informal proofs. Without such formal verification, there's no way to actually reason and ensure the correctness of informal proofs. As we all know, even for famous like math papers and cryptography papers, oftentimes sometimes these informal proofs can contain mistakes. And for AI-generated informal proofs, there can be even higher likelihoods of having mistakes and gaps and so on. So it's really important to combine informal and formal to then, in the end, generate formally verified proofs. Right. So by combining both, also then the models can produce different right informal solutions, and in the end, the correct one will be formally verified. Another important aspect is for scalability for math and so on, is to learn mathematical abstractions. So in particular, again, with the human mathematicians and also with math systems in general, these abstractions such as developing new definitions, lemmas, these are actually very important to be able to solve more complex math problems and so on. And this is particularly an exciting area and directions, I think, for AI for formal math is, and also it's a test for models' creativity as well, is how the models can learn to construct these new definitions, lemmas, and tactics in full-fledged proof assistance. Then this can be utilized then for future future proofs as well. So again, there has been some recent progress in learning and simple proof strategies from agents' own solutions to pass mathematical problems in a bootstrapping fashion. I think this is a really promising and exciting domain, is how we can essentially train models and also proof agents to then better discover and learn abstractions from its own past experience. I think this is really exciting. Also, another sub-area is that there already is a lot of existing mathematical knowledge. How do we actually train the proof agents to better utilize existing mathematical knowledge? For example, to build tailored retrievers for formal mathematical reasoning, and also to be able to handle dynamically growing knowledge base. So again, as we continue this flywheel, we will continue to generate new data, and also with auto-formalization and so on, we'll continue to grow the libraries of definitions and mathematical statements and theorems and so on. And during the proof search, it's very helpful, and also it's very important for these proof agents to be able to utilize these existing knowledge in the library to actually retrieve the relevant theorems and statements and so on to help with the proof search and so on. So an open challenge and also future direction is how do we design better models and retrieval mechanisms that are better tailored for this form of mathematics and using these math libraries and so on. And another interesting question is that how to reconcile the specialist and generalist approaches. So generalist methods, they can identify cross-domain connections, and specialists, they can be effective in individual domains. So we do hope that we can combine these two, for example, by equipping these large language models with domain-specific tools and so on. So far I've talked about open challenges and future directions in two key areas for AI for formal math, data and algorithms. So now I'm going to briefly talk about some open challenges and future directions in two main application domains. One is in assisting human mathematicians for developing better math, and another one is in program generation, code generation, and verification. So, one motivation and value provided with this AI for formal math is that we hope that these tools can really help human mathematicians to make progress in formal math by addressing challenging math problems and developing even new theorems and proofs and so on. So essentially, the hope is that one can use AI to develop better tools in the workflow of these proof assistance to help human mathematicians and work together with human mathematicians to generate proofs for challenging and advanced math and so on. In order for this to be useful, essentially, one actually needs to develop better tools that are actually not just for automatic, generating automate the proof steps, but also actually need to better understand, like doing behavioral studies for how mathematicians use AI, and essentially to develop better, more useful tools for mathematicians. And with the hope that with such tools, one can actually enable these really large-scale distributed collaborations where distributed mathematicians and together with AI tools can help decompose the large projects into different components, and the community can work together to really solve challenging, complex math problems. So another really important application domain is in code generation and program verification. With the goal that really using AI is not just to solve math problems, but more importantly, it actually can help us to enable formal verification, program verification to help build correct and secure programs. So today, as we all know, code generation with LLMs has seen wide adoption. But however, a lot of these, so for example, there has been estimates that for certain companies and projects, like more than 50% of the code is now generated by LLMs. But however, there's a huge challenge in ensuring the correctness and security of the generated code. So for example, passing a few test examples doesn't mean that it's correct. Oh, right. So actually here, the GitHub CEO says the Copilot will write 80% of code sooner than later. So the idea to address this challenge is that instead of just generating code, we should do verifiable code generation, where we generate code and the formal specification and the formal proofs that the generated code meets the formal specification. So here is an example that's, for example, when we want to generate code for this problem to compute the absolute function of the variable. Then we can actually generate the specification and also then generate the proof. So this way, one can ensure the correctness of the generated code. So with this, I have talked about the open challenges and future directions in a number of different areas and application domains for AI for formal math. I think the next 5 years will be really exciting in this domain. We hope to bring the community together to advance AI for formal math and theory improving and develop collaborative open source efforts along multiple dimensions. So in our paper, we also propose milestones and guideposts for the community to work together towards. And also, we hope to bring the community together to develop systematic benchmarks, data sets, algorithms, and tooling in this open source effort. So, motivated are inspired by the autonomous driving space. We also, for AI for formal math, in our paper, we propose a number of milestones and success measures. And in particular, we develop these different levels of AI for formal math. And we also propose benchmarks to help measure at these different levels. And so, for example, in theory improving, we can achieve certain levels listed out here. And of course, there are the more advanced levels where we actually even need a new benchmark and evaluation methodology and so on. And also, similarly, we propose different levels and benchmarks in verified reasoning, in auto-formalization, conjecturing, code generation, and verification. And you can see more details for these in our paper. So I also want to mention that, especially for me, a really exciting direction with this AI for formal math is that we can really develop new approach and solutions to enable security for better safety and security for AI systems. And in particular, recently, with a number of leading AI researchers, including Yashua Benja and so on, we have a new initiative on quantitative AI safety with the goal to develop new approaches to build AI safety with better quantitative guarantees. As a first step towards this goal, in particular, focusing on building provably secure systems, here we hope to to develop new methods to enable us to build secure by design and safe by design systems. So in particular, as we advance the AI capabilities, there is actually a huge risk in security in general, given that the AI can help both attackers and defender side. And in the near term, potentially, AI can actually help attackers more than defenders. And hence, it's really important that we develop new solutions to actually help build more secure systems. And in particular, so there are different ways to improve the security of systems and defend against attacks. In particular, it's important to develop methods to enable what we call secure by design, secure by construction, and this type of proactive defense. So with this approach, in contrast to bug finding and attack detection and reactive defense, we essentially we try to architect and build provably secure systems where so in this case, for a given programming system, we can specify the desired correctness and security properties, and then provide with the formal verification, provide a proof that the system is actually satisfies the desired properties and so on. So due to the the effort and contribution from the formal verification community, I would say we have actually entered the era of formally verified systems. We actually have many different systems, including microkernels, compilers, and file systems, and so on, that actually have been formally verified. But however, a huge issue is that it has been hugely labor intensive to do formal verification for these systems. For example, SER4, the efforts took tens of proof engineer years. And also, as these systems get updated, the proof has to be redone and so on. So the goal is that, so this also motivated our earlier work on using deep learning for theorem proving to automate this process to reduce the manual labor that's needed. And this also is an important motivation for advancing AI for formal math, is that using these new advancements, we hope that we can develop AI agents that instead of just having these agents to play games like Go, but we can actually develop these AI agents that can automatically do automate theorem proving, and together with the capability of program synthesis, instead of just generating code like today without the security and correctness guarantees, we hope that using these proof agents and coding agents, we can actually generate appropriately secure code with proofs. So using this approach, then we can actually use AI to build appropriately secure systems with the code generation and proof generation. And with this approach, we hope to reduce the arms race that's between attackers and defenders, so we can actually generate appropriately secure systems that are resilient against certain classes of attacks. Of course, this approach has many open challenges. So for example, the formal verification approach currently mainly applies to traditional symbolic programs, and it's actually difficult to apply to non-symbolic programs such as deep neural networks. For example, for the deep neural networks components, we don't even have precisely specified properties and goals, such as, like for autonomous vehicles, you want to say that it shouldn't drive over a pedestrian, but we don't even have a precise definition of what pedestrian is. And future systems will be hybrid, combining symbolic and non-symbolic components. And so the current formal verification and secure by construction approach has limited applicability. So, but we hope that with the further advancements, we can develop new approaches and solutions to really help, like using AI to build more secure systems. So with that, so in this talk, I talked about right. I do believe that we are hitting an inflection point where we can use the more advanced AI capabilities to advance for formal mathematical reasoning. And again, you can check out the details of our paper at this link, and we would love to get your feedback. And also with that, I wanted to briefly mention that also this semester, I'm teaching a MOOC, a massive open online course on large language model agents. So last semester, fall 24, we did a version of this MOOC with actually over 15,000 enrolled around the globe. And given the huge success and excitement, so this semester we are doing a new version, advanced large language model agents that particularly focus on reasoning, planning, and coding agents. And also we have a section on AI for theorem proving and formal math as well. So please, you can check it out and enroll it here at this website, agents-learning.org. With that, thank you.
Thanks a lot, Professor Song. It's a very exciting talk about this new area. And given the time, we maybe allow have 2 questions. Is there anyone? And it's, if you have a question, you can unmute yourself. Maybe open up the camera. introduce yourself and then have the question, please.
Hello, Professor Wang and Professor Song. I do have a question. Thanks for your great talk. My name is Shang Gu, and I'm a postdoctor at UC Berkeley. And as you mentioned, large language model shows powerful abilities. So how can we ensure they code security when we use large language models to generate the code?
I see, I see. Okay, that's a very good question. I mean, of course, people currently are also training, these large language models. One is to have it generate more secure code and also try to detect vulnerabilities and so on. But ultimately, I think in order to ensure the correctness and security of the generated code, that's why like I mentioned in the talk, we hope that we should do verifiable code generation, that we can generate the code, the specification, and proof all together, so that we can actually formally verify that the generated code satisfies certain security properties and correctness.
Okay, thanks for your answer.
Yeah, may I ask one question, please? Yeah, so I'm Haitham from the UCL as well. I would like to ask, so you mentioned about the searching, right, through these verifiers and kind of an algorithmic route discovery would be needed there. Can you maybe elaborate a bit more, please? Like, do we need to search directly in the verifiers, or we build simulators of them, or because I suppose it's very slow, but maybe you can help me understand.
Okay, so maybe you're asking the proof search part. So with the proof search, essentially, I mean, there are different ways you can imagine how to do the proof search. So one is, as I mentioned, right, we can have these proof agents and the models to help do the proof search to expand the proof tree. And then in there, essentially, one is that we hope that the models can help suggest the next steps, essentially the next action for expanding the proof search tree, and also ideally maybe we'll have a value model that can help prioritize these different proof states for next steps as well.
Okay, got it. Yeah. Okay, so something like an AlphaGo style of search, but inside.
That's one possibility, right? You can do multi-class tree search, and you can do other things as well.
Thank you.
Cool. Do we have one more?
Yeah. Hello. Thank you very much for your talk. My name is Rasul, and I also work with in Huawei. I had a chance to work a bit with alpha geometry, and my question is this: you mentioned about these integrated tool solutions, such as Lean in case of alpha proof and DDR in case of alpha geometry. But what's your opinion on problems like combinatorial problems, which, for example, alpha proof was not able to solve any of them, and it's quite difficult to translate combinatorial problems, especially challenging one, into a Lean statement so that we could unleash existed integrated solutions. So do you have any ideas how we can cover such topics in mathematics?
I see. Okay, that's a very good question. So for that, right, I'm not very much like I haven't spent a lot of time with these combinatorics questions. So I think these are interesting, directions how we can develop better technologies for those domains.
Yep. Thank you. Thanks. Yeah.
Thank you. Thank you.
All right. I think we have quite a lot of the interesting critical questions. But we don't really have time. Maybe I would suggest that Professor Song already leave the courses and also email. Maybe you can communicate offline. Thanks a lot again for
Thank you. Thanks a lot for having me. Right. Thank you.
Yeah. All right. Yes.